Welcome to this comprehensive overview of computer processors. In this session, we'll explore the fascinating world of CPU, Central Processing Unit, their evolution over time, the role of GPU or graphic processing units, and the basic of SAP1 operation and programming. Whether you're a beginner or looking to deepen your understanding, this guide will provide you with a clear and engaging explanation of these critical components of modern computing. The CPU, or Central Processing Unit, serves as the brain of a computer, executing instruction through the fetch-decode-execute cycle. In the fetch stage, the CPU retrieves instruction stored in memory, typically housed in RAM. This interaction occurs through a network of electrical connection known as the bus system, which enable data transfer. The CPU's ability to access memory depends on its address size. For example, a 4-bit address allows access to 16 memory locations. The data bus carries data, while the address bus transmits data memory locations. When retrieving data, the CPU places an address on the address bus, initiating a memory read or write operation between the CPU and RAM. Registers, which are small and fast storage units within the CPU, temporarily hold data, instruction, and memory addresses. The program counter, a specific register, keeps tracks of the next instruction, ensuring sequential processing unless a branching instruction alters the flow. After fetching, the CPU moves to the decode stage, where it breaks down the instruction into the opcode and operand. The opcode determines the operations such as arithmetic, data movement, or branching, while the operand provides the relevant data or memory location. Branching allows instruction to drop conditionally or unconditionally, enabling decision-making in programs. Some instruction contains immediate value fixed constant or address pointing to memory. During decoding, the CPU configures its internal circuit based on the instruction, preparing for execution. Some modern CPU have programmable decoders, allowing greater flexibility in processing instructions. During execution, the arithmetic logic unit performs operation based on the decoded instruction. For example, if an instruction requires adding 10 to a register, the CPU retrieves the value and the register's content, perform the addition in the ALU, and store the result back. This cycle of processing instruction, executing operation, and updating registers continues in synchronization with the CPU's clock, which dictates its speed. The clock's frequency, measured in Hertz, has evolved significantly from early CPUs like the Intel 4004 running at 740 kHz to modern processors reaching 5 GHz. However, higher clock speeds generate heat, requiring engineers to optimize performance while managing thermal constraint. As CPU advance, memory access delays become a concern. Early processors operated at lower speed, making latency less noticeable. But as performance increased, the distance between components introduced bottleneck. To address this, techniques like pipelining and caching were developed, improving the efficiency. The evolution from simple RISC reduced instruction set computer architectures to more complex CISC complex instruction set computer designs are also played a role in enhancing CPU's capabilities. Over time, CPUs have grown from early models with just 2,300 transistors to today's multi-million transistors design. Future advancement will continue to push the limit of processing power, with development in pipelining, larger bit architecture, and multi-gigahertz clock speeds shaping the next generation of computing technology. Example: adding two numbers in a CPU. Assume a CPU needs to add the number 5 to the value stored in register A and store the result back in register A. The instruction for this operation could look like: add A, 5. Fetch. The CPU's computer counter holds the memory address of the next instruction. The instruction add, 5 is retrieved from memory and placed in the instruction register. The program counter is updated to the point to the next instruction. Decode. The instruction is broken into parts. Opcode. Add, meaning an addition operation. Operand A, 5, indicating that 5 should be added to register A. The CPU determines that the arithmetic logic unit will handle the addition. Lastly, execute. The CPU retrieves the current value stored in register A. The value 5 is added to the register value. 10 plus 5 equals 15. The result 15 is stored back into register A. This cycle repeats continuously for every instruction the CPU processes. The development of the 8086 microprocessor marked a major advancement in computing architecture, particularly with its adoption of the complex instruction set computer design. This shift enabled the CPU to better support high-level programming languages by improving stack-based instructions, which made handling subroutines more efficient. A subroutine is a reusable block of code designed for specific tasks, and when executed, the CPU must store the current memory address to ensure it can return to the main program afterward. This is managed using a memory stock, where data is stored and retrieved in a last-in, first-out manner. However, improper stack management can lead to issues such as stack overflow or program crashes due to incorrect return addresses. The 8086 microprocessor was a key example of CISC architecture, featuring a rich and complex instruction set computer to the simpler, faster, reduced instruction set computer approach. Unlike RISC processor, which relied on straightforward instruction executed quickly, the 8086 CISC architecture allowed the CPU to perform more complex operation directly, minimizing the need for multiple instructions. However, this complexity also resulted in longer execution times, as each instruction could require multiple clock cycles. To mitigate performance slowdown, prefetching was introduced. This technique helping reducing memory bottlenecks by loading the next instruction into memory while current one was still being processed. A significant enhancement to the 8086 was the 8087 coprocessor, which specialized in handling floating-point arithmetic operations such as multiplication, division, and transcendental functions. By offloading this task from the main CPU, the 8087 enabled simultaneous execution of multiple operations, significantly improving processing efficiency. The 8087 processor could handle up to 50,000 floating-point operations per second, allowing the system to execute complex mathematical calculation efficiently. Here's the example. Step-by-step breakdown. Main program execution begin. AX is loaded with 10 and BX is loaded with 5. Subroutine call. The call instruction pushes the return address onto the stock so that CPU knows where to resume execution after completing the subroutine. Execution jumps to the add numbers subroutine. Stock operation in the subroutine. Push AX save the original value of AX onto the stock to prevent overwriting. Add AX, BX perform the addition. AX is equal to 10 plus 5 equals 15. Pop AX restores the same value of AX from stock. Rep retrieves the return address from the stock and resume execution at the instruction following call add numbers. Returning to the main program, the result 15 is stored in CX. The program continues the HLT instruction halt execution. The IBM personal computer, introduced in 1981, played a crucial role in the widespread adoption of the 8086 variant. The 8088. The IBM PC revolutionized the personal computing industry with its affordable pricing and user-friendly design, quickly gaining popularity. Microsoft PC DOS operating system developed under contract for IBM further solidified the company's dominance in the software market. The success of the IBM PC led to a surge in compatible hardware and software, establishing the PC architectures as the industry standard for decades. Even today, the influence of the 8086 microprocessor remains evident in modern personal computers and servers, showcasing its lasting impact on technology. The 1980s were a crucial decade for CPU design, introducing innovation that laid the foundation for modern computing. The evolution of multitasking, memory management, and processor architecture enabled the transition from single-task system to complex multi-user environments, shaping the future of personal computers and operating systems. Multitasking is the ability for multiple programs to run concurrently on a single CPU. This paradigm shift greatly improved CPU efficiency, stability, and security. Early forms of multitasking. Multiprogramming from 1960s to early 1970s. Early computers used batch processing, switching between tasks when waiting for input-output. Time sharing. Late 1980s to 1970s. Introduced real-time switching between processes, enabling multi-user environments. Through multitasking. From 1970s to 1980s. Operating systems like Multics and Unix pioneered robust multitasking model, influencing modern OS development. Type of multitasking. Cooperative multitasking. Each process voluntarily gives up CPU control. If a process gets stuck in a loop, it can crash the system. Preemptive multitasking, the modern standard. The OS forcibly switches processes based on time slices, prevents a single program from hogging the CPU. Next is memory management and protection. With multitasking, multiple processes will share memory without interfering with each other. This is handled by the Memory Management Unit. Key features of an MMU. Memory protection prevents one process from accessing another's memory, improving system security. Privilege level restricts lower privilege program from modifying critical system areas. Virtual memory allows program to assume they have more memory than physically available. Uses pages to break memory into fixed-size chunks that can be swapped to disk when needed. Conclusion. The 1980s laid the groundwork for modern computing by refining multitasking, memory management, and CPU architectures. The Motorola 68K and Intel 86 introduced fundamental innovation that still shape modern systems today. While the 68K was user-friendly with a flat memory model, Intel's 86 series pioneered hardware-supported multitasking, which eventually became the industry standard. A GPU, graphics processing unit, is a specialized electronic circuit primarily designed to accelerate the rendering of images, videos, and animations. While originally designed to handle graphics-related tasks, modern GPUs are increasingly used for a wide range of non-graphical computations such as machine learning, scientific simulation, and cryptography due to their parallel processing capabilities. Key function and characteristic of a GPU. Graphic rendering. The primary function of a GPU is rendering graphics on the screen, particularly 3D graphics, which require intensive computations for tasks such as texture, mapping, shading, and lighting. The GPU offloads this task from CPU, allowing the computer to focus on other functions. Next is parallel processing. A GPU is composed of thousands of smaller cores capable of handling many calculations simultaneously, making it built for tasks that can be split into multiple parallel operations. This architecture enabled GPUs to process large datasets in parallel, significantly speeding up the tasks like image processing, machine learning models, training, and data analytics. Next is shader and pipelines. The GPU pipeline consists of various stages that process graphical data. This includes vertex shaders, geometry shaders, and pixel shaders, each handling different aspects of graphical rendering. Shaders are small programs that run on the GPU defining how objects are drawn, shaded, and illustrated in a scene. Memory. VGRAM or VRAM is used by the GPU to store textures, frame buffers, and other graphical assets that it processes. VRAM is optimized for high-speed data transfer to keep up with the GPU's processes demand. In addition to graphic data, GPU can also handle non-graphical workloads such as data used in deep learning models, ray tracing, and real-time graphics. Modern GPUs are capable of ray tracing, which simulates how light interacts with objects in a scene to create realistic lighting, shadow, and reflection. Real-time rendering has become more achievable with advanced GPU, making game and simulation look more realistic while still maintaining playable frame set. Types of GPUs. Discrete GPUs. These are separate components typically installed as a dedicated card in the system. Next is integrated GPUs. These are built into the same chip as the CPU. While they are less powerful than discrete GPUs, they are sufficient for tasks like web browsing, office work, and video playback. Lastly, professional GPUs. These GPUs are designed for specialized workload like professional 3D rendering, video editing, and scientific simulation. Examples include NVIDIA Quadro and AMD Radeon Pro. SOP1 refers to Simplified Academic Processor 1, which is a conceptual, simplified model of a computer processor used to teach the fundamentals of computer architecture and machine-level programming. It is commonly used in educational setting to demonstrate how a basic microprocessor works. SOP1 operation. The SOP1 architecture is based on a single-cycle operation, meaning Each instruction is executed in a single clock cycle, making it easy to understand the basic concept of how a CPU processes instruction. SAP1 is composed of a variety of registers, control unit, and a bus system. The control unit manages the sequence of operation by issuing control signals to the different components. It uses the set of control lines to dictate the operation performed. Memory. SAP1 typically uses a simple memory unit to store instruction and data. Each memory location can store 1 byte of data, and the memory is organized into sequential address location. Bus system. A bus is used to transfer data between components such as the memory, registers, and ALU. To write programs for SAP1, we use a very basic machine learning consists of binary instruction. Each instruction is typically represented by a binary code that is composed of an opcode, operational code, and the operand or address or immediate value. For example, let's say you want to add two numbers stored in memory location 10 and 11 and store the result in memory location 12. Instruction 1. Load the number from memory location 10 into the accumulator. Opcode for LDA or load accumulator is equal 0001. Operand for memory location 10 is equivalent to 1010. Machine code is 00011010. LDA 10. Instruction 2. Add the number from memory location 11 to the accumulator. Opcode for add is equal to 0010. Operand for memory allocation 12 is equal to 1011. Machine code 00101011. Add 11. Instruction 3. Store the result from the accumulator into memory allocation 12. Opcode for STA or store allocation is equal to 0100. Operand for memory allocation 12 is equivalent to 1100. Machine code is 01001100. STA 12. Instruction 4. End the program or MOP. Opcode for NOP is equivalent to 1111. Machine code is 111111 NOP. The machine code for this simple program will be 00111010. LDA 10. 00101011. Add 11. 10001000 STA 12. 111111 NOP. Programming model in SAP1. Load values from memory into the accumulator. Perform arithmetic operation, add or subtract on data in the accumulator. Store result back to memory. Conditional/unconditional branching to control the flow of the program. The programming for SAP1 is typically done in machine language or assembly for simplicity, given the minimal nature of the processor. In conclusion, SAP1 is a fundamental educational model used to introduce students to basic concepts of computer architecture, operations, and programming. It demonstrates the core principle of how a CPU fetches, decodes, and executes instruction, with its minimalistic design serving as an effective teaching tool. Programming in SAP1 allows students to understand the relationship between the machine code and the hardware operations of the CPU.